Welcome back, everybody, to AP Chemistry. We're in Unit 7, taking a look at Section 4 and using our KSP values to figure out if something is going to be soluble when it is dissolved in some kind of solvent. Typically, it's going to be water. So, pretty simple. I think you guys are going to find this is not too bad. The solubility constant is calculated by your concentrations in your Q value. So basically what we're going to be doing is taking a look at how does that solubility constant compare to our Q values. And just keep in mind that a large KSP typically means more soluble, but we'll be proving this math-wise. Okay, so let's just look at some examples of this. Like I said, I think you guys would pick up on this pretty fast. And we're going to be finding the solubility of something, the solubility of lead to iodide, given the KSP value of 1.4 times 10 to the negative 8. So the key with all of these is figuring out, first of all, what it will dissociate into. Remember when we're finding Q values, that any solid or liquid would act as one particle. It's not dissociated, so that's my concentration is 1. It doesn't impact anything else in there. I take a look and I see with my balanced equation that I've got one of these, but I do in fact have 2 iodines in there. So that's going to affect my Q value. So what does this look like math-wise? Well, your KSP value is going to be a function of 1.4 times 10 to the negative 8, and that will equal my unknown of my lead, so that's my unknown X, that's my unknown value for that, and there's only one of those, so it's to the 1 power, and we see that my iodine is also an unknown, and because the coefficient is 2, it's a 2x, and that will be squared. Now, technically, that is all over 1 because of my lead in there. So it's just products concentrations over the reactants concentrations like we've always done. So if I expand this out math-wise, I'll end up with 1.4 times 10 to the negative 8. That will equal 4x cubed. Okay, so 2 times 2 is 4, and it's going to be squared. Then 4x squared times x is going to end up with 4x cubed. So if I divide both sides by 4, I'll end up with x cubed equals 3.5 times 10 to the negative 9. Leaving that, if I take the cube root, I'll end up with 1.5 times 10 to the negative 3. So the question originally was, what is the solubility? Okay, so that's how many moles per liter we would end up with. So pretty straightforward. That's how you do a problem using given a solubility constant. Now, we can also flip it around to figure out what, if I know the concentration of one thing, I can figure out the concentration of the other if I was given that value. So let's see, we've got, first of all, we have to figure out what the compound is and what the equation is to find my ratios. So this is going to be aluminum hydroxide. Notice that aluminum has a +3 charge and hydroxide has a -1 charge. So that means to be balanced out as a solid, okay, that acts as one particle, I would have AlOH3. But that's going to dissociate into my aluminum ion, that's aqueous, and that will also dissociate into 3 of my hydroxide, that's going to be aqueous. Okay, so now I can plug things in, and I see that my KSP is 2 times 10 to the negative 32nd. That will equal my aluminum concentration, that's a 3 there, and there's only one of those, times my hydroxide concentration, and that should be 3 of those hydroxides because my coefficient is 3. All right, so if I see those things in there, I end up with plugging values in. This was 0.5. This is my unknown, but notice it's going to be an x, a 3x, I should say, with that. So 3x cubed, if I'm going to cube my 3, 3 times 3 is 9, times 3 is 27. That's 27x cubed times my 0.5, and that will equal my 2 times 10 to the negative 32nd. Okay, so if I'm getting all this derived out, x cubed, again, multiply and then divide to get them off onto one side. X cubed ends up being 1.48 times 10 to the negative 33, and take the cube root, x ends up being 1.14 times 10 to the negative 11th. And that's my concentration then of my unknown with my hydroxide. All right, so that's using just another permutation and seeing those. I have just 3 more problems for you with this. We want to know the molar solubility of silver sulfate in water, first of all, and then what if I don't use my silver sulfate in water, I instead dissolve it into silver nitrate, okay? So there's 2 parts to this. So let's take a look at the water component first. This will follow exactly what we were doing before. We have silver sulfate. So silver, remember, is a +1 charge. Sulfate is a -2 charge. So if I was going to write this out, this is going to be a solid, and I'll get my silver ion, +1, but notice I'll have to have two of those, won't I? I'll have a sulfate, -2, and this is what it would dissociate into if it was going to be aqueous, okay? So now, what do I do from there? Well, I see that I have a 1.2 times 10 to the -5th is my KSP value. That will equal my unknown, because that's what we're solving for, but that will be squared, won't it? Then we take a look at my sulfate. That's also an unknown, but I only have one of those. All right, so if I square this, I have 4x squared times x, so I end up with, in all of this, 1.2 times 10 to the -5th. That will equal 4x cubed. Again, divide both sides by 4. Then I'll take the cube root. I end up with x being 1.44 times 10 to the -2nd. In other words, 0.0144. Okay, that is going to be my solubility. So that's going to be a label of moles per liter. That's if I dissolved in water. But if I dissolved it in silver nitrate instead, silver nitrate is going to be a little bit different. Okay, the reason it's different is because it's going to be adding one silver into that, one silver ion. So it kind of changes things up a little bit in that it offers one more in there. Notice also that because this ends up being an equilibrium problem, notice my KSP is going to be pretty small. So really, I can ignore that or disregard that value. Let's take a look at what happens when I put this into equilibrium then. I end up, first of all, my 1.2 times 10 to the -5th. That will equal, now here comes that addition of my silver nitrate. That's going to add in 0.10 molar. Okay, silver nitrate has only one silver to offer in there, so it's a 1-to-1 ratio. So 1.1 molar added to my X. Okay, and so that ends up being, remember my silver was a 2X, so I square that. Now I'm going to multiply that times my X value. Now notice this is sulfate, so the silver nitrate doesn't do any contributions. So that part will remain the same. Now, remember what I said. This is a small value of KSP, so I can disregard this contribution. And so I just basically square this and get this. And so I end up 0.1 squared is 0.01. So I end up with a 1.2 times 10 to the -5th. That will equal 0.01x. Okay, and so from there, I just solve for my x, and that my x ends up being a 1.2 times 10 to the -3. Okay, so just added one more factor, which is actually what we were kind of expecting with that. Okay, so pretty straightforward in doing a problem like that one. Two more, and we're going to be seeing now if I have two different things that I mix together in different volumes. Okay, now with this one, it's a little bit different. We're not just taking one thing and dissolving it. We're actually adding two things in here and finding out if it's going to precipitate. My KSP value is this. Okay, I'm not finding my solubility anymore. I'm actually trying to find, did I add enough to actually knock some out of solution? So that means that I have to start with a balanced equation. I have my barium chloride. I'm going to be mixing that with my sodium sulfate. Now my products then are going to end up being barium sulfate and sodium chloride. Okay, if I was going to be balancing it, I'd need two of these. The question is this going to precipitate? So it's a question there. Is that going to make a solid off of it? So I have to figure out how much barium I have in the first place, how much sulfate I have in the first place, to see if it's going to be precipitating. Okay, this isn't as tricky as a person might expect. I just have to keep track of what I'm going to be analyzing. So let's first of all track my barium. Okay, I see that I have a 0.02 molar solution. That means that I have 0.02 moles of barium for every 1 liter of solution. But I don't have a solution, a liter of solution. I have 75 milliliters. So remember, that's a 0.075 liters. Okay, so the question is, how much barium do I have in here? Well, if I do that math, I end up with a 0.0015 moles of barium. Now, if I want to know its concentration, you got to be careful because I have 0.0015 moles of barium over how many liters total? Well, I have 75 milliliters plus 125 milliliters. That's 200 milliliters total. And so the key to this one is realizing I have 0.2 liters total. Okay, so that will end up being 0.0075 molar barium chloride. Now you know how strong that is. Now we take a look and let's analyze the sulfate component. And remember, that's a -2 charge. And so again, same game, I have 0.04 moles of sulfate per liter of solution. But I don't have a full liter, I have 125 milliliters. That's 0.125 liters. Okay, so in just that scenario, I end up with a 0.05 moles of sulfate. So this, if I combine the two in there, I end up with 0.2 liters total. So what's the concentration? That ends up being a 0.025 molar, and that's of my sulfate. So now I can plug in for my Q value. Let's see what ends up happening. And remember, I'm looking to see, is my Q going to be more or is my K going to be more? I see that my Q is going to be a function of my barium. And let's double check. I see that I have, in my equation, I have 1 barium. So that's to the 1 power. And I see also my sulfate in there, don't I? That's going to be a -2. And notice my sulfate is to the 1 power as well. And so now I can plug in my values. I have 0.0075 times my 0.025. So what's my Q value? My Q value ends up being 1.9 times 10 to the -4th. Okay, so if I look at that and compare, I saw that my KSP value is 1.5 times 10 to the -9. So my Q is definitely larger than my K. So therefore, yes, this forms a precipitate, because it favors the products. Okay, that's how we figure out with those things. So let's take a look at one more problem with that, a little bit more complicated in determining that Q value. Now make sure that you do answer the question yes or no, but also back it up with the math. So let's take a look one more time. Very similar type of problem. This time we're asking, does the magnesium precipitate? So I'm going to be mixing my magnesium nitrate, MgNO3. Magnesium has a 2 charge, nitrate has a 1. And I'm going to mix that with sodium hydroxide, 1 and 1. So I'm going to get out of this magnesium hydroxide. Hydroxide's a -1 charge. Hydroxide's -1. Magnesium's a +2. And I'm going to get also sodium nitrate. Now all nitrates are soluble. That's not what we're analyzing. We're analyzing my magnesium to see, does it precipitate? Okay, that's the big question. So now I've got everything set up and we play the exact same game. I have to figure out, first of all, how much magnesium is present. So let's go with my magnesium. That's a 2+. And so let's see, we started out with a 4 times 10 to the -4th moles of magnesium for every liter of solution. But I don't have a liter of solution once again. I have 0.1 liter. And so I end up with 4 times 10 to the -5th now moles of magnesium. Now be careful, because that's moles of magnesium, and we have to get that into my my liters of solution. So moles of magnesium divided by 0.2 liters of solution. Okay, and so that ends up actually dividing that answer by 2, and so it divides it by 0.2, and so 4 times 10 to the -5th divided by 0.2, that will give me 2 times 10 to the -4th, and that's the strength of my magnesium. Okay, so let's now take a look at the other component of that, which would be my hydroxide, because that's the thing I'm going to be analyzing here. And I see that my hydroxide is also going to be, this one's going to be 2 times 10 to the -4th moles of hydroxide, and that's a liter of solution. Once again, I don't have a liter of solution, so that's 0.1 liters, and so I end up with 2 times 10 to the -5th moles of hydroxide. Okay? Now, again, that's 2 times 10 to the -5th, but that's divided by 0.2 total, because I had because I had 100 plus 100, and that will give me 1 times 10 to the negative fourth. Okay, that's the strength of my hydroxide. Now take a look at what happens here, because I got to find my Q value. My Q value, looking at this, I see I have 2 hydroxides in there, so that's what's going to throw all this a little bit. I have my magnesium, there's one of those, and I have my hydroxide, but there's 2 of those. Okay, so that's going to be squared in there. So then I end up plugging in 2 times 10 to the negative fourth, and that's going to be times 1 times 10 to the negative fourth, but that's going to be squared. Okay, so if I square that and multiply it by 2 times 10 to the negative fourth, I end up with a value of 2 times 10 to the negative 12th. Okay, and what do we see? We see that this is my K value, this is my Q. My K value is 8 times 10 to the negative 12th. So that means that my KSP is actually larger than my K, or than my Q. And so what does that mean? That means no, there is no precipitate being formed. So make sure whenever we see questions like this that we do answer the question directly, yes or no, but then back it up with the math with that, and we'll be able to get the full points. Okay, so that's going to solve the last of those problems. And as we take a look, we're wrapping up the unit with this. We'll see some NIMSY problems. We will be doing some multiple choice review problems in there to get us ready for the test. But other than that, that is it for equilibrium and the entire Unit 7. Good luck to you guys.